So my name's Lindsey Smith. I work for British Steel. I'm going to talk about a HYPEREUCTECTOID rail today. It's non-heat treated. We call it HP335. I've not touched anything. Go back. Okay. It's an as-roll product. As a company, we metallurgically engineered it to be both wear, RCF resistant. Typical rail microstructure, it's made up of perlite. There's layers of two different materials. You get the ferrite, which is iron, it's ductile but soft. So the cementite, so you get the iron carbide, so it's hard and brittle. But the combination of the two gives resistance to both wear and rolling contact fatigue. We add alloys into the HP335 to improve that basic structure, so we get away without needing heat treatment, which is the traditional method to employ, sort of improve the rail to improve rolling contact fatigue and wear resistance. I'm pressing it. Okay, so in-service performance, so that's primarily my job when I work with British Steel, is I go out on track and I do measurements and look at the performance of the rail. So we have extensively monitored this product in the UK with the national operator, Network Rail. We had a 5-year trial and we looked at 7 sites with Network Rail and 1 with a light rail site. Network Rail reported savings of just under £250,000 over a 5-year period, which was what the R260 was previously lasting for. If you extrapolate that up to what we now expect the HP335 to last at one particular site called Het Mill, we expect to have a saving of around about 1.25 million. The trial sites that we monitored showed that RCF wear and corrugation resistance were improved by a factor of 3. We also found that resistance to plastic flow was very good. Out of all these trial sites, what we didn't look at was heavy hull. So when I talk about heavy hull, in comparison to American railroads, it's slightly different. So our maximum axle tonnage in the UK is 25 tons. So we had some HP335 installed on a heavy hull site. It's at a power station. It's a private site in the UK. It's a 200-metre radius curve. The particular section of track we're measuring is a max line speed of 15 miles per hour. It comes around the curve. It has to wait at a signal. So all that weight is on the low rail. So unsurprisingly, it was suffering from low rail plastic flow and low rail rolling contact fatigue. When I went to the site before they installed HP335 to look at the R260, it's like, well, when did you install it? And they were, I don't know. Anyway, so we looked at the branding on the rail, and the rail age on the branding was 2012, 2013, so we can surmise for that it was in 2 to 3 years on the R260. So this is what it looked like on the R260. So this is on the high rail, so some extensive rolling contact fatigue. And on the low rail, well, you can see the low rail plastic flow towards the field side on the R260. I'm only going to be talking about the findings on the low rail today on the HP335. I've not got time to talk about everything, so if you are interested in the results on the high rail, you'll have to refer back to the paper. So this is an example of the spooling that we saw on the R260 with large chunks coming out. The issue with that is ultrasonic testing. With these large chunks coming out, what you can't see with an ultrasonic tester is what's growing underneath. So at that point, the rail has to be taken out of service because you can't guarantee, as an example there. So the ultrasound can't penetrate through that crack, so it will not detect the deeper crack underneath. So we now move on to what I've found with the HP335. So this is just looking at the low rail. You can see at 15 million gross tons that we started to develop some rolling contact fatigue around there and about there. Just very, very small initiation. 23 million gross tonnes, so I approximately go back every 3 months to this site. So we started to see some more developing around the centre of the head. I typically call this snakeskin effect, which is low rail, roll and contact fatigue. 26 million gross tonnes, we can see that there was some more developed on the HP325. You've got sort of 3 strains. You've got some running that way, some running that way, and then some going that way. At this point, we recommended that they ground. So previously, with the R260, they never ground the R260. But with the harder rail, we recommended that they implemented a preventative grinding regime. They weren't able to do that. They could only stretch as far as a corrective grinding. So they're now grinding the site annually. So this was taken pre-grinding, the picture at 26 million gross tonnes, and I went back a week later and looking at the same position. They didn't quite remove all the RCF, but overall the site was pretty clear. So we've carried on monitoring the site after they've ground it. We're now at 38 million gross tonnes. Got the RCF come back. So if you remember back to the slide that I showed earlier with the big chunks coming out, well, that was actually taken at 35 million gross tonnes. You can just about see it underneath the number. So we've had a life extension here combined with the grinding in that rail had to be removed from service. We're now at 38 million gross tonnes. Yeah, we've got some RCF, but it was due to be ground again at the next service. So looking at the profiles, so if you look at the right one, that's the R260. And you can see the measured rail profile is the red one. And you can see the low rail plastic flow. Head wear was 4.3 mil at that point. So if you look at the HP325, which is on the left, no plastic flow to be seen. So we've pretty much cured that problem from that particular site. Head wear at 2.2 mil, so half of what the R260 was, but bear in mind the HP325 does include the grinding. I don't have the grinding figures, the amount of material that they removed to hand, but it is in the paper. So if we start looking at sort of the life cycle costing that I worked out with the company. So on the bottom axis, we've got traffic in MGT. The side axis looks at the whole life cost, so that's taking into account inspection and grinding and replacement. So the black line is the R260. The big jumps that you can see is where they've had to replace the rail. So the orange line is looking at the HP325. So the little jumps is where they've had the grinder in every year. So if you look over the period of what we predict the HP325 is now likely to be in service, we're predicting a £92,000 cost saving over what they had previously in terms of the R260. So I also looked at the predicted lifetime. We're now expecting the HP325 to just last under 250 million gross tonnes on the low rail compared to just under 50 with the R260. So there's been significant sort of lifetime extension of the R260 at this particular site in the UK, just looking at whole leaf freight. So just to summarise, we've monitored HP325 within a heavy haul environment. It's performed very well, particularly in terms of the plastic flow, the crown profile retention. They do have to grind it now with a grinding regime where they didn't have before, but even in taking into account the costs of grinding, they are getting that significant life extension. And overall, around about 7 times life extension. And that's the end of the slides. Thank you.